Now we have to talk about basic probabilities. Probability is the heart of statistics. Particularly at the level we're dealing with it, we want to know outcomes and their probabilities. So we're going to keep this as basic as possible because I realize that probabilities can get very complex. We want to make sure we have the basic understanding of this. So let's start off very simplistically. Let's say we're going to flip a fair coin. Well, we know that there's heads and tails, so there's our fair coin. And we're assuming that it's not weighted or anything like that. Now, if I were to ask you, what are the odds that if I flip this coin, it'll land on heads? Right? Or in other words, what if I were to ask you the probability of heads? You probably would say it's 50% chance. And then I might ask you, well, how do you know that? And your answer would most likely be, well, if you flip the coin, it's going to land on either heads or it's going to land on tails. Those are the only real choices that we have. And you would be correct. And the way you came to that conclusion is the heart of probability. So by definition, probability is the number of options that meet our condition divided by the number of equally likely outcomes. And that's the basic formula that we'll be dealing with. And that's the basic formula throughout probability. The number of options that meet our condition. In this particular case, heads. There's only one. That's the only option that meets our condition. What are the number of equally likely outcomes? Well, there's heads and there's also tails. So we have one that meets our condition divided by the two equally likely outcomes, which would give us the 0.50 converted into a percentage of 50% chance that when we flip this coin, it'll land on heads. Now let's say we decided to go with the probabilities that we call tails. Okay, well the probability, that's a P, of tails, well that would also be 50%. Why? Because the number of options that meet our condition is 1. The number of equally likely outcomes is still 2. So that would also give us the 50% chance. Now, if we were to take a look at this and say, okay, well, 50% chance, we might say that, well, as you flip a coin, half the times it's going to come up on heads, half the times it's going to come up on tails. And in theory, that is the case. However, you could flip a coin twice. So let's say we flip this coin twice, and the first flip, we ended up with heads. And the second flip, we also ended up with heads. Now, does that mean that it's not a 50-50 shot? No, it doesn't. We have an issue here that has to do with n. We only have an n of 2. If we increase n as the value of n, let's say it's not 2, let's say we do it 100 times, or maybe we'll have n equaling, let's say, 100,000 times. As n increases, it's more likely to break down into a 50-50 split. So as n goes up, you're more likely to come out to the true probabilities. If you have a small n, well, in statistics and in research, we would say you could have a sampling error. Right? At any one given point, even 2 given points, it's going to be heads or tails. It could be heads and heads, it could be tails and heads, it could be heads and tails, it could be tails and tails. But if we increase that, and we increase n, we're more likely to see the true probabilities. Okay, so now what if we were dealing with, I don't know, how about dice? And we wanted to know what's the probability of rolling a 4. Now let's remind ourselves what the formula is for probability. Right? Probability is the number of options that meet our condition, in this case 1, the number 4, and the number of equally likely outcomes, which in this case is now 6. So the probabilities, 1 is the 4, right? And then there's 6 equally likely outcomes, which would give us 0.17, which would equal 17%. So it's a 17% chance of rolling a 4 on a 6-sided dice. Now, of course, yes, obviously, we're assuming that the dice is not weighted or shaved or anything like that, that this is a fair die. Now, we can expand this a little bit. Now, let's say we decide to know what's the probability? What's the probability of rolling a 4 or a 6? So what's the probability of rolling a 4 or a 6? Well, the number of options that meet our condition is a 4 and a 6. So we have 2 of those divided by equally number of likely possibilities, which would be 6. So 2 divided by 6, you'll see it'll give us 0.33, which would be a 33% chance of rolling a 4 or a 6. Now, what if we were just wanting to know, let's say, what's the probability of rolling an even number? So let's say probability of even. Well, if we're to continue with this, we could say, all right, well, there's 3 even numbers, and there's 3 odds. So we have a total of 6 equally likely outcomes, which will give us 50%, a 50-50 chance of rolling an even number. Now, what if we were to say, all right, what's the probability? The probability of rolling a 2 and a 6. What's the probability of that? A 2 and a 6 with only one dice, or one die, I guess I should say. Well, you can't roll a 2 and a 6. It's not possible. So that's 0. Divided by 6, this will tell you that there is no chance of rolling a 2 and a 6 with a single die. These here are what we would call mutually exclusive. And by that, if we have something that's mutually exclusive, they cannot happen at the same time. So those would be mutually exclusive. Now, we were talking about probabilities with one die. But what if we had 2 6-sided dice? And we wanted to know, what's the probability of rolling a 10 with 2 dice? In order to figure this out now, we're going to have to take a look at the possible combinations that can occur when you have 2 dice. So if you're going down to Atlantic City or you're going out to Las Vegas and you're going to play craps, which is a 2-dice game, you'll see that the board is laid out in a certain way that some bets are more likely to occur than others. So how do you know what's more or less likely to occur? Well, let's draw it out. We're going to illustrate it first. If we have dice 1, which I'll write here in red, what are the possibilities with rolling 1 die? Well, you have a 1, a 2, 3, 4, 5, or a 6. Now, what's the possibilities on the second dice? Well, you would also have a 1, 2, 3, 4, 5, and 6. So on each one of those, you have 6 equally likely outcomes. So what do these outcomes end up looking like? Well, I'm going to draw it in a table sort of format just so we can illustrate what this actually looks like. So let's say, let's draw a line through here, and we'll draw another line. We're going to kind of make like a small table, which I guess you could do in your notes if you want to, or you can just follow along. So we want to see exactly what this is going to look like. To see what the combinations are, so we can tell what would be more likely or what's less likely to happen when you're playing with 2 dice, when you're running these probabilities. And I'm going to change the ink color one more time just so we can kind of keep this straight. Let's use the purple. So if we get a 1 on the green die and a 1 on the red die, that would give us a 2. If we had a 1 on the green and a 2 on the red, we would have rolled a 3. 1 on green, 3 on red, we would have rolled a 4. 5, 6, and 7. Now you're probably already seeing how this is turning out now. But as you have, these are the combinations that we're looking at. What are the combinations that we could possibly roll by giving, if the one die, let's say green or red, rolls one particular value versus if the other one rolls a particular value. And as you see, this paints for us all possible combinations. I'm just going to fill the whole thing in here, but you probably can see what this is already looking like. The mistake would be to think that it's something out of 12. It's a 1 out of 12 or a 2 out of 12, and that's not it at all, actually. As you're looking at this, you're probably seeing that it's actually out of 36. So as we take a look at this, you say, all right, now what are we dealing with here? Well, we want to know the probability of rolling a 10. Well, how many possible combinations or ways is there to get a 10? Well, we can roll a 6 and a 4, which would give us a 10 here. We can roll a 5 and a 5, which would give us a 10 here. Or we can roll a 4 and a 6. So there's only 3 possible ways to get a 10 with 2 dice out of 36 possible combinations. So in doing this, let's say we had 3 possible combinations out of 36 possible equally likely outcomes, which would give us 0.083, which is repeated, so we could say 8%. It's an 8% chance of rolling a 10 with 2 dice. And if you're a gambler, if you go down to Atlantic City and you're playing craps, you'll see that you'll crap out at 11, which is down here. There's only 2 possible. That's a 2 in 36 chance, and 7, which is the most likely roll, because that has the most possible combinations of them all. So keeping in mind that with the 2 dice, now you have to factor in all possible combinations. And depending on the neighborhood you grow up in, maybe you're familiar with CeeLo, where it involves 3 dice. Well, now this complicates it more, because now you have to not just look at the possible combinations with 2, but now with 3. And if you're keeping up with it and you're probably a little bit ahead, you're probably seeing that we can have 6 with the 1 dice. And with the second dice, we could also have 6. And the third dice, we could also have 6. But this is a multiplication problem here. So 6 times 6 times 6, which gives us 216 possible combinations. And if you're playing CeeLo, you'll know that if you roll what they call the devil's number, right? 666. In CeeLo, that's the highest possible roll. There's only 1 possible combination for getting a 666. So that would be, so what's the probability of an 18 in CeeLo? Well, there's only 1. So that's a 1 divided by 216 equally likely outcomes. And that's going to equal 0.0046. So if we were to turn that into a decimal, or I'm sorry, into a percentage, at that point, we're talking about 0.46%, about a 0.5% of rolling a 666 in CeeLo. So let's take a look at another type of area where probabilities are sort of in our, I don't want to say everyday life, but they're around us a lot. And that's cards. We play cards. Some of us do anyway. Now, let's take a look at the probabilities involved in a deck of cards. So, I'm going to spread this all out. If we were in a classroom, I would just simply, pick on some people about this, but we're not, so let's just take a look. That's the basic outline within a deck of cards. Now, you'll notice that we have 1 and 2 full suits of red. These are the hearts over here. See the heart? You have diamonds, and they're red. And within each suit, you have your ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. So you have 13 cards in each suit, 4 suits, 3 reds, and 3 of them, 2 red and 2 black. Right, so we have our clubs and spades. So if we were to, let's say, we want to know what's the probability of a red card picked at random from a shuffled deck. Well, you could take a look right off the top and you can see that if we have a total number, a total of cards n equaling 52, in each suit you would have an n equaling 13. So if we were to take a look and say, all right, well, what's the probability of picking out a red card? Well, in each of these we have an n of 13, n equaling 13, and that's the same with these here, n equaling 13, n equaling 13. Well, the number of cards that meet our criteria is 26 because there's 2 13 card suits. So we would have 26, and that's out of a total of 52 cards. And that's going to give us, if I get my pen working again, I don't know why I just stopped, but that's going to equal 0.5. So at random, picking a card out is a red card out of a deck of 52 is a 50-50 shot. 50% of the deck is going to be red. So that's like flipping a coin. Now, what if we were to say, okay, what's the probability of picking out a heart? So we'll pick out a heart. Well, we could take a look and we say, all right, well, the hearts are here, right? These are the hearts. How many hearts are there? Well, there's, I should close that parenthesis, huh? There's 13 hearts out of 52 cards. So if we reduce that fraction, you see it's 1/4, which would tell us that it's 0.25 or 25% chance. The probability of picking out a heart out of a randomly shuffled deck is a 1 in 4 shot, or 25%. So what if we were to say, doing another one, let's say we were to go probability of, I don't know, a jack. What's the probability of picking out a jack? Well, now we have to take a look. Here are our jacks. All right, we have our jacks here. Let's see if I can erase that line for the hearts. Oh, good. Oh, I can do that. Those stuff doesn't always work as nicely as that. I'm glad that did work. So we're going to pick out a jack. Well, we can see that there are there's 1, 2, 3, 4 jacks in the deck. So there's 4 cards, right? There's 4 options that meet our conditions out of how many cards total? Well, 52. So what is that going to equal? Well, we can take a look at that, and if we want to, we could reduce the fraction a little bit here. So that becomes a 1 in 13, which would give us 0.076 or 7.6% chance of pulling a jack randomly out of a deck of cards. Now, what if we were looking at the probability of pulling out a jack or a heart? So it's a jack or a heart. Well, we already established that there are these jacks here, and we know we were dealing with hearts before, so let's recircle our hearts. And we know that looking at the way the diagram is, we have 13 hearts and we have 4 jacks. So we have our 4 jacks plus our 13. However, this jack here is in both categories, so we have to eliminate it from 1. So we have to subtract out 1 because we don't want to count that jack twice. And then divide that by 52, which would give us 16 out of 52, which would then equal 4 out of 13, which would equal, that's a 3 by the way, 0.3076 or 30.76%. So just under 31% chance of pulling a jack or a heart. Now all the probabilities we've been talking about are all basically discrete variables, right? So when we look at flipping a coin, that's going to be heads or tails. When we're rolling dice, if it say it's 1 die, it's a 1 out of 6 chance of any given number being picked. So if it's 4, where the odds of rolling a 4, that's 1 out of 6. And if a card, what's the odds of pulling a jack? I mean, just pulling a jack. Well, that's a 4 out of 52 chance. So these would be effectively discrete. And if you remember from your notes, take a look back at some of the older videos or consult your notes. Discrete can have some but not all values between the highest and the lowest. But what happens when we're dealing with continuous variables? What do probabilities look like then? So what does this mean if it's a continuous variable? Well, believe it or not, we actually already covered that. If we take a look at the normal distribution again, and we take a look, we say, okay, here's our mean, which is the 0 point if we're going by z-scores, right? And that's mu. And then we have 1 standard deviation, 2, 3, and 4 above the mean, and 1 below, 2 below, 3 below, and 4 standard deviations below. The empirical rule tells us how much of a population is between any of these points, right? So you can go back and review that video or take a look in your notes at the breakdown or look at the Z-chart. The Z-chart will break that down as well for us. The same thing works with probabilities here. This whole thing is a population. Now, if we were going to say out of this whole thing, if it's a continuous variable, meaning it can have any value between its highest and its lowest, the probability of finding any one given data point in this continuum is exactly 0. So we speak of it in ranges. So for example, when we talk about, how much rain is going to fall, they'll tell you, well, between 4 to 6 inches of rain, because it's a continuous variable. To get any one point is not possible. So with probabilities, and let's do it with IQ, since that's a known parameter. So we'll put IQ up in here because that's what we're going to be dealing with. And we know that the mean of the population, mu, is 100. And we know that IQ has a standard deviation equaling 15. So now we want to know, let's say we're going to talk about it in z-scores. And we're going to be working with these z-scores at the bottom on the number line. So then let's say the probability, we want to know what's the probability of finding a z-score at random that is greater than or equal to 0. So the probability of finding a z-score that is greater than or equal to 0. Well, the 0 point is the mean. So that's going to be here. This whole half of the graph, this would be the greater than or equal to point. Well, that's, as we know from the empirical rule, that's 50% of the population. So that probability is 50%. So it's 50% if you picked a person at random that they would be equal to or greater than the mean. Or a z-score picked at random equal to or greater than 0. Let's say we were looking for a z-score between 2 points. Now the same way we would have calculated the area or portion of a population between 2 points, that's the probability. So we've already done this, we're just using a new application. So let's say it was the probability of having a z-score, so having a z-score that is greater than or equal to 0, but is less than or equal to 1. That would be this area here. Greater than or equal to 0, but less than or equal to 1. And we know from our empirical rule that this is 0.3413. Oh, we lost the 1 there for some reason. Which would tell us that that's a 34.13% chance of finding a person who has a z-score between 0 and 1. And you can look at it as raw scores as well. And again, this is nothing new. We've already done this with the z-scores and the portion or percentage of a population. We're just using it as a new application. So you can think of it as 34% of a population is within this range here, right? 34% of a population. Also at random, picking a person randomly, it's a 34% chance that they'll be in that range. And if you run that through for a little bit and just sit on that, you might see it kind of makes sense, because this whole thing is 100% of a population, right? So from end to end, we're talking about 1.001 or 100% of the population. So this breaks down as probabilities. But let's look at it as going with the raw score using IQ, right? So with IQ, we know the raw score here would be 100. And then each standard deviation going up would be an additional 15 points. Going down, you would subtract an additional 15 points. So let's say we wanted to take a look at it. Let's say, I'm going to change the color just because I want to. Let's say the probability of having a raw score, so we'll put X to represent the raw score, an X that is greater than or equal to 85, but is less than or equal to 115. So then you should come down here and take a look. Well, we know that if we're going above, one standard deviation above the mean here, which is 100, would be 115. And one standard deviation below, which would be 15 points below the mean, is an 85. So we're talking about from here to here. Now, if you're doing this on a worksheet and you're working with the raw scores, you're probably going to have to convert the 115 and the 85 to Z's. It might make it a little bit easier, especially if it doesn't fall neatly on the standard deviation. So convert your raw scores to Z's, and then the probabilities are exactly the same from there. Right? So we would have about 68%, I'm estimating, but 68% chance of picking out a person at random who would fall between an 85 and a 115. And I guess another example, let's say we have the probability of finding a raw score, an X, that is less than or equal to 100. Now, if we turn the 100 into a Z, we would see that the Z for that equals 0. So that's here. And less than, well, that's coming down this way, and that's half the graph. That would be a 50% chance. So you're not doing anything different or differently than we did in the previous videos. We're just using a new application. So we can think of it not just as the portion of a population or percent of a population, but that's also the probabilities of pulling someone at random from the same population.